$51 is next. Okay. So we got M1 and M2 here. So this is M1, and its mass is equal to 1.3 kilograms. This is M2 over here, and its mass is equal to 2.8 kilograms. So these are important, okay? These are important. And the question says, what are the, what's the value of the acceleration and what's the tension in the cord? No problem. So, because we have two objects, we're going to do the system first, and after the system, we're going to do the individual blocks and see how it looks. So let's talk about the system. Well, the first thing I want to do, whether I'm examining the system or each block individually, is we have to draw a force diagram that makes some sense. So, when I do the green one, okay, when I do the green one here, the thing I notice is that the Earth is pulling it down with, right? So this is mg is equal to 13 newtons, okay? For the red one over here, this is m2g is equal to 28 newtons. Okay. Oh, sorry, I forgot. This is m1g. Okay. Now, what's pulling them upward? So this string is pulling them upward. Now, if this one is heavier than this one, the whole thing is going to go. It's going to rotate this way. So what does that tell you about this guy? This guy's going to not only go down, but he's going to accelerate down. But what does that mean about this guy then? He has to accelerate up. So when I go to draw, this, I know that the tension in this cable, has to be greater than this weight because this guy's accelerating up. But over here, the tension in the cable has to be less than this guy because this guy's accelerating down. And it's one piece of string, so the tension in the cable has to be the same. So when you draw this, the tension has to be bigger than this one, smaller than this one, but equal to itself. That's the deal. So let's do the system. Okay? This 13 and this 28, they're fighting against each other, right? So when I talk about the system, I know that the acceleration of the system is equal to the net force on the system divided by the mass of the system. And by the system, I mean both blocks. So to get the acceleration of the system, take the F net, which is this minus this, right? So it's basically m2g minus m1g all over. And how to express the mass of the system? m1 plus m2. And luckily, I have everything that's on this side, so I can just plug and chug this bad boy. m2g is 28 minus m1g is 13. And this is 2.8 plus 1.3. What do we get here? 3.66 meters per second per second. Now, that means this one's accelerating up at 3.66, this one's accelerating down at 3.66, right? So each block is doing its own thing. So that's where we are for the system. Now, the next question is find the tension in the cable or the rope or whatever. So let's do the green block, M1. The acceleration of 1 is equal to the net force on 1 divided by the mass of 1. So I know that the acceleration of the system is the acceleration of block 1. That's like the cool thing. So I know that this is acceleration 1, we're going to put 3.6 in. How do I express the net force? Well, I'm going to come over here and I'm going to look at this. I'm going to do big minus small. So I have T minus M1G all over M1. And now I have everything except for the tension, and I can plug a chunk. So this is 3.66. Tension minus the weight, which is 13, over 1.3. So the tension, according to this, is 17.7 newtons. Now, what I like is this is 13, so if this tension is 17.7, it's bigger than 13, that works for us. As a check, to see if we have done this correctly, let's do M2. So the acceleration of 2 is equal to the net force on 2 over the mass of 2. We know the acceleration, we'll get there in a second. But this one, I'm going to do big minus small again, so I can use the positive 3.66. So this one's going to be M2G minus T all over M2. 3.66 is equal to 28 minus the tension all over 2.8. And if you plug and chug this, you're going to realize, and we can do this, like this is 2 times 3.6, so this is a little more than 3, this is a little bit less than 3, right? So 3 times 3 is 9, and 28 minus 9 is 17, so that's a good estimate. So when you do this, you know you've done it correctly if you solve for the tension using both elements, right? And it's in here and they're the same. So 17.7 is less than 28, that looks good. Okay, 57. 57. Fifty-seven's got a sweet diagram to go with it. Hold on. 'So this is a 30-degree ramp angle. Okay. So I'm going to look at this one here. Okay. We'll call that one purple one. We'll make this one a blue one. The key to this is going to be drawing the force diagrams in a way that makes sense. And so, I want to write the masses. So we're going to call this one M2, and its mass is 2.3 kilograms. call this one M1, and its mass is 3.7 kilograms. And the first thing it asks is, what are the magnitudes of the acceleration of each block, the direction of the acceleration of the hanging block, and the tension in the cord? So there's no friction. If you just let this go, does this block accelerate up the ramp or down the ramp? And then consequently, would this one accelerate down or accelerate up? And then what's the tension in the cord? And what's the value of that acceleration? So the key to this is once you have a sweet picture, you've got to draw a good force diagram. And we have two elements, so we're going to do two force diagrams. So this one's a little bit more challenging, so I'm going to draw this one. Now, we know the Earth pulls it straight down. We call that mg. Okay? And then the ramp pushes it perpendicular. Right? That one's the normal force. There's a cord pulling it this way. That's the tension. Now, I don't know how much that is, so we're not going to put it in yet. But I do know that we're going to use XY on the ramp like this. So I'm going to break this up. This component here is mg sine theta. This component here is mg cosine theta. Is that good? I mean, I think it looks good. And then this one here, we know it has its own mg, m2g. Oh, these are all m1. Sorry. m1, m1, m1. There. And then we know that there's some tension here. Now, I don't know whether this object is accelerating up or down. If it's accelerating down, the weight's going to be bigger than the tension. If it's accelerating up, the tension's going to be bigger than the weight. I just don't know yet. Here's how you figure it out. We have to think about this as a system. Okay? So let's use the system concept. So I know the acceleration of the system is equal to the net force on the system divided by the mass of the system. Okay? So I want to know what forces are causing this thing to accelerate. Well, think about it this way. The only force that's making this thing slide up and down the ramp are the tension and the mg sine theta. And the thing that's making this one accelerate up or down are the tension and the m2g. But the thing about the two tensions is it's just one string. So this tension is in this direction, this tension is in this direction. And so the two tensions always cancel themselves out in the system. So what that leaves us with is a battle between the m2g, which is trying to make the whole thing accelerate this way, and the m1g sine theta, which is trying to make it accelerate this way. So let's get some values for these. It's just this one, actually. So this block is 3.7, so its weight is 37 newtons. And then because this is 30 degrees, I know that this is going to be half of that. So what is this, 17, 18 and a half? So this component is 18.5 newtons. How much does this thing weigh? It's 23 newtons. So which is bigger, the 23 or the 18 and a half? Obviously the 23, which means that the 23 wins, and so this whole thing is accelerating this way. So this bad boy is accelerating down, this one's accelerating up the ramp. And that's okay for me, because actually that's pretty good. So that looks good there. This one looks good here. So how do I get the net force on the system then? Well, the net force on the system is going to be the 23 minus the 18.5. And what's the mass of the system? Well, it's 3.7 plus 2.3. This is 23 minus 18.5. That's got to be 3, so 4.5 divided by 6. Oh, 4.5 divided by 6. Is that what I got? Yeah. 4.5 divided by 6 is actually 3/4, so 0.75 meters per second per second. And that acceleration is this one, it's up the ramp, and this one's down the ramp. So I like that because this one's accelerating down, so the tension is less. All right, and let's use that same thing we did before. Okay, let's use that same thing we did before. If I want to do this guy, I know that the acceleration is equal to the net force over the mass. So if the acceleration is 0.75, the net force here is going to be m2g minus t all over m2. This mg is 23 minus the tension over 2.3. And the tension there is equal to 21 point, what did I write? Uh, 0.75 times 2.3. Basically, it's 21.3 newtons, which is cool. And we know that it has to be less than the 23 because this one's accelerating down. Can we do it for the blue one? I bet we can. I know the acceleration is equal to the net force over the mass. Now, because this one is accelerating this way, I'm only going to use the net force in that direction. So what I have for the net force in this direction is I know it's accelerating up, so the t is bigger than the m1g sine theta. So it's this force and this force that contribute to that acceleration. And they're in opposite directions, so you need to subtract. We know that t is bigger, so I do t minus that. And this is all over m1. So the acceleration is the same because it's all tied together with a string. This is 18.5. M1 was 3.7. I will do it in real time for you. So 0.75 times 3.7, okay, plus 18.5. All right, we got t is equal to the same, 21.3